Thank you for the opportunity to give this talk. All right, so today I will talk about vibrations of simplicial sets. In particular, I will talk about left vibrations. And so I'll just write this down. Vibrations, simplicial sets. So in general, vibrations are an ingredient in the model structures of various kinds, and in particular, the general goal, I guess, of this part is to get some hold of the homotopical data about infinity one categories using the notion of vibration of categories, and I guess ultimately the real model structure which affords a great deal of homotopical information about the simplicial model for infinity one categories. So, let's write this down. The goal, I put it in quotes because, I mean, there are many goals, of course, and vibrations, categorical vibrations are interesting on their own, but to some extent, the main purpose of this concept is to get homotypical data about infinity one categories by studying vibrations of various kind. This in particular leads to the real model structure, which is interesting because the weak condition, or the condition that a simplicial set presents an infinity one category in the real model structure, is just the vibrancy condition, where infinity one categories or quasi-categories are precisely vibrant objects. So let's start with some examples. The most basic one was, of course, already covered, but we have the notion of a confibration. And confibrations are defined using this Lifton property. So for any Horner inclusion, we must have a lift in this diagram. And I will denote it sometimes by symbol, which is translated into the phrase that either iota has the left lifting property with respect to P, or dually P has the right lifting property with respect to iota. Of course, we also have similarly defined weak condition, which is also stated in these terms. But also we can dualize the setup and get the notion of an energy map between simplicial sets. So a map iota between two simplicial sets. Iota is energy if for any P, which is a confibration, we have the lifting property. So there exists a lift. And also another example is when we consider First of all, we consider inclusions of boundary spheres into simplices, and we get, by considering maps which have the right lifting property with respect to such inclusions, we get the notion of a trivial fibration. And once again, this can be stated in terms of model categories. So this would be precisely the trivial fibrations in the standard Kant-Quillen model structure on simplicial sets. And the maps with right lifting property with respect to boundary sphere inclusions. All right, but we want to do something a bit more categorical. So there are three additional concepts that incarnate this categorical nature of various maps between simplicial sets. So the first one is the concept of left fibration. Left fibration is a map F such that it satisfies the right lifting property with respect to all Horn inclusions, where we allow I to vary not from 1 to n-1, but from 0 to n-1. So we allow the inclusion of the Horn with index 0. And we require the right lifting property with respect to all such maps. And dually, we can define a right fibration as a map such that we have the right lifting property with respect to all Horn inclusions for indices from 1 to n. Finally, we have the notion of an inner fibration which is quite expectedly just the maps which satisfy the weak Kant condition. So, of course, we can dualize this and obtain the notions of a left Hamilton map is a map such that is a map iota such that iota satisfies the left lifting property with respect to all left fibrations. And similarly, we can define a right Hamilton map just by saying that we need the lifting property with respect to right fibrations. And finally, an inner Hamilton map if we say that it just satisfies the left lifting property with respect to all inner fibrations. All right, so let's try to get an understanding of what these conditions translate to categorically. So what does it mean for a map to be a right fibration? Let's consider a map from an infinity 1 category X to infinity 1 category S. Then this map is a right fibration if and only if X is an infinity one category over S, Fibrations group points. And I didn't give any precise definition of this concept yet, but we can start to naively think of what does it mean for one category to be fibered in group points over another. Well, in I guess the simplest terms, it just means that a fiber of this functor is a groupoid for each object. Of course, it's a much weaker condition than what it actually says, but nevertheless, we can try to understand it at least at this level. So first of all, let's just look at what this would mean in the usual one categorical setting. So assume that you have a map of categories, a functor, and you have an object. Then you can try to take a fiber over this object. Well, first of all, what is a fiber? Well, it's just a category with objects that project into this object C. So if the functor is denoted by P, then we get that the objects are precisely the ones that project into C, and morphisms in the fiber are just morphisms in the over category D, such that P of F is equal to the identity map on the object C. So now we can try to do the same thing. Yeah, and of course, if in the usual one categorical sense, the functor exhibits D as a category fibered in groupoids over C, then such a fiber always will be a groupoid. So one category theory, if D is fibered groupoids over C, then F is a group. Okay. So maybe let's try to get something similar for infinity categories. So first of all, we know that we have this condition that there must exist a lift. What does it mean concretely? Well, let's take n equal to 2. Then we know that the horns we must look at have a form like this. So it's delta 2, 1, and delta 2, 2. Remember, we're looking at the right fibrations. So we're interested in these two horns. Okay, let's try to say something about the fiber. So, of course, in the setting of infinity categories, it is interesting to consider simplices of various dimensions. But let's once again concentrate on the simplest case, where you just have a vertex, so the zero simplex. And we want to once again find a fiber. Well, it's quite easy to find a fiber. Even in the infinity categorical setting, it's quite easy to identify it within T. So the fiber would just consist of simplices in D, such that the result of the projection of the simplex, so the composition, belongs to the simplicial subset generated by this single vertex. So it's a degeneration of the zero simplex. So I'll denote this simplicial subset by star underlined. Okay. So now let's consider some morphism in the fiber. Just one morphism. So it's a map from delta 1 to D, such that P of tau is equal to the identity map, or the identity 1 morphism in the infinity 1 category star. Okay, so we want to show that tau is actually inverted. Well, the similarity between 1 category theory and infinity category theory here should give us the fact that the fiber is an infinity groupoid, or just a concordance. And, well, it's quite easy. We just draw a triangle. So here we would have the identity on the codomain of tau. And this is, of course, a horn of the form which we allow. So concretely, it's this one. It's, lambda 2, 2. And we know that this horn admits a filling because, of course, we have just a map that factors to zero-dimensional simplex on the bottom. So we have this here. And we have a map from this horn to D, which means that we have a lift and we have an inverse to tau. It's a one-sided inverse. So we're not completely done. We didn't show that tau is an actual isomorphism up to homotopy. We didn't show that it is an equivalence. But nevertheless, we can try to show that actually psi that we constructed is also an inverse from the other side. So right now, we only know that psi is a right inverse. But we can actually try to show that it's a left inverse as well. And once again, we can just use horns. So let's draw S3 simplex. We get something like this. And the missing face is the out face. So the rest of the plane of my tablet represents the missing face. Yeah, and we can assign morphisms to edges of this tetrahedron. And the way we do this is the following. So we assign psi to 1, 2. We assign the identity on the domain of tau to 1, 3. And also we have tau here. And we have tau here. As is quite clear, here we also have the identity on the domain. So now it is quite clear that all the faces except the missing one are filled, which means that we have a lift, which shows that actually psi is also the left inverse. Is in fact left inverse of top. I don't know. Maybe I'm going too slow and this is too elementary. So if that's the case, please let me know. Okay, so I hope that this simple example somewhat illustrated that indeed, when we consider right fibrations, we get a notion of infinity category over another infinity category, which is fibered in group parts. So we somewhat showed that the fiber over each object, at least, is an infinity group part. And we have the following hierarchy between various kinds of fibrations. So the smallest class is, of course, the class of trio fibrations. Then we have cut fibrations. Then we have left fibrations. Then we have Cartesian fibrations. Here we have right fibrations. Here we have Cartesian fibrations. And here we have categorical fibrations. And finally, we have, as the largest class, we have inner fibrations. And as it turns out, if we couple a class of fibrations, so for example, left fibrations or right fibrations, with the corresponding class of anodyne maps, we get a factorization system. So so the point is that if you take anodyne maps of a certain kind, so either inner anodyne, left anodyne, or right anodyne, and fibrations of the same kind, you get a factorization system. What that means is that, well, concretely, it means that for any map from X to Z, there is a factorization where Q is anodyne of this kind, and P is fibration of the same kind. The way it is proven is by using the small object argument, which I want to briefly recall right now. So the small object argument is a very important part of the theory of quantum categories, and in fact, I guess, goes back to Quillen. The point is that if you have a certain set of maps, which you can consider as something of a generating of vibration, so for example, for simplicial sets, this would be the boundary sphere inclusion or boundary of the simplex inclusion to the simplex itself, or a boundary sphere inclusion into the disk of the corresponding dimension for topological spaces, you can generate a factorization system for which you have a notion of cofibration, or which is obtained by taking transfinite compositions of push-outs for the elements of your generating cofibrations. And a trivial fibration, which is a map which satisfies the right lifting property with respect to all the maps in your set of generating cofibrations. And essentially, the way this construction proceeds is very similar to what we see in topological spaces. So you basically just glue stuff onto the image of your map to obtain what you need. But let me write this down. I guess it's pretty hard to follow without anything written down at all. So I will state some version of the small objects argument, which is, of course, not very general. There are far more general setups. I guess you can find them almost anywhere, including the Lurie's book, where the setup is much more general than what I will explain right now. But the gist of it is pretty simple. So assume that C is a locally small category. Just says that home sets are sets and not classes. C is co-complete. And I is some subset in the class of morphisms in C, such that domains of all maps from I are compact. What does it mean? Well, it just means that the home functor from this thing commutes with sequential colimits. So if you have a sequence of maps, an infinite sequence of maps, and you take a colimit of this diagram, this commutes with taking a colimit of the corresponding home sets. And I guess the meaning of the term compact here is quite clear, because this is precisely how compactness works for topological spaces. You just say that, okay, if a space is compact, then certainly you can just say that if you have this sequence of maps, then the image of a compact space is contained at a certain finite stage. Okay, so then under these assumptions, for any f, which is a morphism in C, there exists a functorial factorization of the form G to some other object to Y. So this class of maps consists of transfinite pushouts of elements of I, and this consists of maps with the right lifting property with respect to with respect to I. So once again, if we consider boundary sphere inclusions as the set I, and your category C is the category of topological spaces or category of simplicial sets, then you get that RLP of I is just the class of trivial fibrations, and cell of I is just a class of, well, for topological spaces, that would be the class of relative CW complexes, or for simplicial sets, this, I guess, would be just the class of monomorphisms. All right, so let's give a sort of a proof for this statement. So how do we do this? Well, we start from the following set, and it is indeed a set because we assume that the category is locally small. So we just take all possible maps I from our set I large, and we consider commutative diagrams like this. So we have this map we want to factorize, and we just consider commutative diagrams. Then we can form a huge object or a huge map between two huge objects. So we take the co-product of all maps I from our I large, and we iterate over the set S1. So please note that although maps I might be the same, they might be different in S1 because S1 consists not just of elements of I, but of these commutative squares. So S1 might be quite a bit larger than I large. So yeah, we take this and we obtain another morphism, which looks like this. This is just the notation. Then we can define Z0 as X. And we have a diagram like this, just a push-out square. So we take this push-out map, we take Z0, and we consider a push-out. So we get a push-out like this. And this is by definition Z1. And of course, we have the map F here, or F0. We have the map from L I over F into Y, which is induced by the maps from these commutative squares. And this means that we, of course, have a map from the push-out. So we obtained a kind of pre-factorization. So it's not an honest factorization of the map because we don't know that this map is a push out of we don't know that these two maps have the desired properties. For example, we don't yet know that this map has a lifting property. But nevertheless, we obtained some kind of a factorization. And that's basically how the small object argument proceeds. So we obtained Z1, and we have this new map that we call F1. F1 goes from Z1 to Y. Then we can apply the same construction to this map. So we obtain Z2 and another map F2 to Y. And then we can iterate it until we get such objects and maps for all natural numbers. Then we can define Z omega as the co-limit of the corresponding directed system. And of course, we have a map f omega into y by the universal property. And the claim is that this is the map that we wanted. And the way it is proven basically just follows from, well, the statement follows from the following observation. So consider this map f omega from z omega to y, and basically the only thing we need to prove is that we have this Lifton property for any I in I large. But we already know that the domains of all maps in I large are compact objects, which means that maps from these objects commute with taking directed limits over with taking sequential colimits. So the existence of this lift basically just follows from the fact that this diagram occurred somewhere at a finite stage. So we know that we constructed this z omega from all possible Lifton problems like this, or all possible commutative diagrams like this. And we know that after each step, we sort of added a lift. We just forcefully added the lift by considering this push out. So this is a lift. It might be a lift to the next stage, but since we considered a colimit, this means that for each pair K and L and the map I between them, we actually have a lift. And this lift comes precisely from this map here. So let me maybe reiterate. So we know that we have a lift for I into z n plus 1. Because z n plus 1 is defined by a push out like this, and we can consider a lift like this. But then we just say that since we considered a colimit, and we know that the domains of all maps in I are compact, we can just apply this logic to see that we have a canonical map from K to z omega, and this induces this map from L to z omega, which is the desired lift. And of course, as you can easily see, all arguments we did here were completely factorial, so this factorization is factorial. Okay. Yeah, I don't know if there are any questions about this. Maybe let me write down explicitly what happened for simplicial sets and boundary inclusions. So let's assume that our set I consists of this. Then Z1 is formed from Z naught by attaching all disks to maps of simplicial spheres such that after applying our map F or F naught from Z naught to Y, the spheres in question become contractible. So once again, assume that you have a sphere inside of Z naught that is mapped into something contractible in Y. So you get something contractible. Then the point of constructing Z1 is that we just attach a disk to the sphere. So in a sense, this procedure is just a mapping cone, but much larger. So the point is that I guess you trade a very convenient and simple construction of a mapping cone for functoriality. Because of course the construction of a mapping cone is non-functorial, but the construction of this thing is completely functorial, which I guess is the advantage here. Yeah, okay. So now let's talk a bit more about left fibrations, and in particular their motivation from the ordinary category theory. So let's start from a small one category D. D is a small one category. And assume that you have a map from D into the category of group points. So it's a functor. Then we have a Grothinger construction for this functor. And what the Grothinger construction does is that it produces a new category over D, C chi over D, using the following data. So objects of C chi are pairs consisting of objects in the initial category D and objects in the image of D under chi. Yes, this is why sometimes the Grothinger construction is also called the category of elements construction, because you just take elements. And the morphisms are defined as follows. So assume that you have two objects in your category C chi. Then a morphism consists of two things. So first of all, it's a morphism in D between D and D prime. And also it is a morphism in the image of D prime under chi, which is just a morphism between this image and this object. And of course, note that actually you can drop the assumption that you're considering functors into groupoids and just consider functor into the category of small categories. Also note that we can consider a very specific choice of chi, which is just a functor from groupoids to groupoids given by the identity. And for this, we of course also have Grothinger construction. Well, I mean, modulo some minor problems, like the category of groupoids not being small. But I guess you can always fix it with some gadget like Grothinger universes and make sense of it. The point is that if you apply the Grothendieck deconstruction to this identity functor, you obtain a category over groupoids, over the category of groupoids. And it is quite easy to see that, first of all, the description of this category is completely analogous, but basically it's just a category of pairs where you consider groupoids and just objects in them. But also, it is quite easy to see that actually, if you consider the Grothendieck deconstruction for an arbitrary functor chi, you have a pullback square like this. So in a sense, the Grothendieck deconstruction is just a very familiar construction from, I don't know, differential topology or topology where you have a classified space of some kind of object. So, for example, classified space of a group, and all fibrations are classified by maps. All principal fibrations with the structure group are classified by maps into this classifying space. So in a sense here, the category of groupoids plays the role of the classifying space for fibrations in groupoids. And yeah, that's in a sense the point. So now let's get a little more concrete and relate this to the notion of a left fibration that we discussed earlier. So let me first of all state properly what does it mean for a category to be co-fibered in groupoids. So since we're considering left fibrations, it will be co-fibered in groupoids, not fibered. A category is co-fibered in groupoids if the following two conditions are satisfied. So category C over D is co-fibered in groupoids if, first of all, for any object C and any morphism eta from f of C to D in the base category, there exists a lift. So just a very natural categorification of the notion of fibration from topology, such that f of eta wave is the same as eta. And the second condition is that for any morphism like this, for any object in the category C, we have a bijection. This is slightly trickier, and I hope I will be able to explain what this means more geometrically in a moment. So first of all, let me explain what this map is. So assume that you have a morphism F from here. Then, of course, if you have this map eta, you can map it into a pair like this. You can map it into eta F eta. And also you can just apply the functor F and get an element from the Hom set on the right. So basically what this says is that if you have a morphism in the fiber, this means that it induces an isomorph. Well, basically it means that it is invertible. So maybe let's look at it both from the viewpoint of infinite category theory, and also let's see why this is indeed the case. But before that, let me just briefly mention that, of course, if you have a growth construction, then this gives an example of a category which is co-fibered in grouplets. So the key result here, which relates it with the homotopical stuff we discussed earlier, is the following proposition. So assume that you have a functor between two ordinary categories, then C over D is co-fibered in grouplets if and only if the nerve of this functor is a left fibration. And the proof actually shows quite a bit about the meaning of this condition for a functor to be co-fibered in groupoids. So first of all, we note that n of f is automatically an inner fibration. And this is not that interesting. I mean, the condition on being an inner fibration is basically just asserting that your functor is categorical in nature. So you're basically just allowed to take compositions. But what is interesting is that from this easy observation, we see that we need to only lift one horn. So we can consider a lifting problem like this. And we need to show that the lift exists for any n greater than 0. So let's look at some cases. So for n equal to 1, the corresponding horn is just a point. So the problem becomes to lift a morphism into the total space, I guess, into this infinity one category. And of course, we can do this because we have the first condition of a category being co-fibered in groupoids. It's lifted condition. Well, for n equal to 2, this is just the surjectivity condition. So we take a horn like this, and we take a diagram here like this, and we just observe that if this is filled, then we can find f like this. So this probably draw it. This. So f exists because of the lifting property. And finally, for n equal to 3, this is slightly trickier, but this is just the injectivity condition for the map of home sets. Why? Well, because if you have two maps, two elements of the home set that are mapped into the same thing, then you can take a horn like this, and you'll see that actually f is supposed to be equal to f prime, which shows injectivity. So this is injectivity, this is injectivity, which shows that indeed one direction is clear. The map between the home sets is an isomorphism if the map is a left fibration. But the converse also is quite simple, because we know that for functors between nerves of two one categories, there is a uniqueness, because we don't just have a weak Kant condition, we have also an additional uniqueness condition. Essentially, there exists a unique feeling, which means that if you know that you have an isomorphism like this, an isomorphism between home sets like this, then it automatically guarantees that this extends to simplices of arbitrary dimension. I guess that's everything that I wanted to say today. Thank you so much for listening to this. And I apologize for any mistakes that I made. Okay. All right. See everybody in a week.